Namaste my dear students, welcome to physics online class. In the last class, we have derived an expression for potential energy of a dipole in the presence of external electric field. Now let us solve one problem based on that concept. The problem is two charges plus 3.2 into 10 power minus 19 coulomb and minus 3.2 into 10 power minus 19 coulomb, that is equal and opposite charges, are placed at a distance of 2.4 into 10 power minus 10 meter from each other. This arrangement is situated in a uniform electric field of 4 into 10 power 5 volt per meter or Newton per coulomb. Find electric dipole moment, then electric potential energy at the equilibrium position, and finally energy required to rotate the dipole through 180 degree from the equilibrium position. Okay, position of equilibrium. So let us solve this problem. Now if you consider the magnitude of charges, it is equal to 3.2 into 10 power minus 19. So if you list the given quantities here, magnitude of charge Q is equal to 3.2 into 10 power minus 19 coulomb. Okay, then charges are placed at a distance of 2.4 into 10 power minus 10 meter. Now the separation between the charges is nothing but it is the dipole length. Therefore straight away I can write dipole length. We represented dipole length as 2a. 2a is equal to 2.4 into 10 power minus 10 meter. Okay, minus 10 meter. In a uniform electric field of strength of electric field or magnitude of electric intensity is given, that is equal to 4 into 10 power 5 volt per meter. Okay, 5 volt per meter. Okay, so first quantity, first of all, calculate the electric dipole moment. Direct expression, electric dipole moment is represented P by P and its magnitude is given by dipole length into magnitude of charge, that is P is equal to 2aq. Substitute the values. 2a is given. Okay, it is not a, it is 2a itself. 2a is 2.4 into 10 power minus 10 into magnitude of charge, that is 3.2 into 10 power minus 19. Okay, minus 19. So that is equal to multiply 2.4 into 3.2, 7.68 into 10 power minus 10 minus 19, total it is equal to 10 power minus 29. Okay, so the unit is coulomb meter. Dipole moment 7.68 into 10 power minus 19 coulomb meter, that is dipole moment. Second quantity, electric potential energy at the equilibrium position. What is electric potential energy at the equilibrium position? In the last class we derived that this equation, potential energy of dipole is given by minus Pe cos theta, or it is the dot product of dipole moment vector and electric field vector minus Pe cos theta. Given that, or we have to calculate the potential energy at the equilibrium position. What do you mean by equilibrium position? Equilibrium position means angle between the dipole moment vector and electric field, theta is equal to 0 degree. That is called equilibrium position or stable equilibrium position. Therefore substitute the values. Minus P value, we just calculated the P value, that is dipole moment vector, 7.68 into 10 power minus 29 into strength of electric field is 4. Okay, 4 into 10 to the power 5 is the electric field, Pe cos theta, so that is cos 0. So that is equal to 7.68 into 4 minus is there, minus 30.72, that is 7.68 into 4, into cos 0 is 1, cos 0 is equal to 1, therefore into 1, 30.72, 10 power minus 29 plus 5, that is 10 power minus 24. It is the potential energy, therefore it is expressed in terms of joule. So this much joule is the potential energy. Okay. Answer for second question, potential energy. I think it is clear. Dipole moment vector, then potential energy at the equilibrium position. If you want to calculate the potential energy at the unstable equilibrium position, that is angle between electric field and dipole moment vector is equal to 180 degree, put theta is equal to 180 degree. If it is asked to calculate the potential energy of dipole at a position when angle between P and E is equal to 60 degree, instead of theta put 60 degree, you will get potential energy at that angular position. Okay, potential energy at that angular position. Next, last one, that is third one. I think it is clear. Third part, solution for third part. Energy required, find the energy required to rotate the dipole through 180 degree from the position of equilibrium. That means now angle between P and E is equal to 0, that is at a stable position. From that position, dipole must be rotated through an angle of 180 degree. That means that is shifted from stable equilibrium position to unstable equilibrium position. Under that case, what is the energy required? Or in other words, we can say that what is the amount of work done, or what is the change in potential energy? For all these things, the questions, answer is same. So when a dipole is rotated from one angular position to another angular position, change in its energy, potential energy is given by PE into cos theta naught minus cos theta 1. Here theta naught represents initial position, angular position, theta 1 represents final angular position, and for that rotation, due to that rotation, what is the amount change in potential energy of dipole, that is given by this expression. Now this is change in potential energy, or it is also equal to work done in rotating the dipole, or it is also equal to energy required to rotate the dipole. You can calculate for any angle of rotation. Okay, what is the change in potential energy? Expression is this one. What is the amount of work done? Same expression. What is the energy required? Same expression. Okay, so let us calculate the energy required. So energy required in this case is equal to P is, we just calculated the value, that is 7.68 into 10 power minus 29, that is dipole moment vector, into strength of electric field is 4 into 10 power 5. Okay, 4 into 10 power 5 into cos, from which position? From the position of equilibrium. That means in this case, okay, right here, see, the dipole is rotated from the position of equilibrium, that is here initial angular position is 0 degree because it is the stable equilibrium position, through 180 degree. That means new angle theta 1 is equal to 180 degree. Theta 1 is equal to 180 degree. Okay. If it is asked to calculate the energy required to rotate the dipole through 60 degree, theta naught is 0, theta 1 is 60 degree. So substitute the values. P is 7.68 into 10 power minus 29 into electric field is 4 into 10 power 5 into cos 0 minus cos 180. Okay, cos 0 minus cos 180, that is equal to 7.68 into 4 into 10 power minus 29 plus 5, that is 10 power minus 24 into cos 0 is 1 minus cos 180 is minus 1, that is 1 minus of minus 1. So that is equal to, now 1 minus into minus plus 1 plus 1 2, 2 into 4 8, 8 into 7.68, it is equal to 61.44 into 10 power minus 24. Again it is energy required or change in potential energy, or it is the work done. So therefore it is expressed in terms of joules. So work done is equal to 61.44 into 10 power minus 24 joule. That is the answer for third question. Okay. Okay, I think it is clear. Let us continue the discussion in theory part. The next concept is dielectrics. Dielectrics. Dielectrics are nothing but, or dielectric is nothing but, it is non-conducting material. Non-conducting materials are called dielectrics. Now in case of dielectrics, two categories are there, that is based on the distribution of charges, positive and negative charges in case of molecule. Before discussing the categories in dielectrics, let us consider the case of a substance. We know that every substance is made up of molecule. If you consider a molecule of a substance, it is made up of atoms. We know that the constituent particles of an atom. Inside an atom there will be neutrons, charge is 0, protons positively charged, and electrons, that is negatively charged. That means if you consider a molecule or if you consider an atom, in case of an atom, number of protons present inside the nucleus is equal to number of electrons revolving around the nucleus. You have studied this concept in atoms chapter, right? So number of protons is equal to number of electrons. That means total positive charge carried by an atom is equal to total negative charge carried by the atom. So atom is electrically neutral, that is the meaning. Okay. Now if you consider a molecule made up of three atoms, just for example 3 atoms, an atom, in case of an atom, number of protons is equal to number of electrons. If you consider a molecule made up of 3 atoms, okay, 3 atoms, in case of molecule also, number of protons will be equal to number of electrons, because it is made up of atoms in which number of protons and number of electrons are equal, isn't it? Now these protons and electrons are distributed inside this molecule. Okay, distribution or these charges, protons and electrons, will be distributed all over the space inside the molecule. Now if these 3 are the nucleus, then positive charge of this atom here, positive charge of another atom, positive charge of another atom. Positive charges will be distributed like this nucleus. Next, electrons will be revolving around the nucleus, that means negative charges will be distributed like this. Now in case of this molecule, we can consider 2 points, that is center of positive charge. Okay. In case of a molecule, we can consider 2 points. One is center of positive charge. That means we can imagine a point at which entire positive charge of this molecule is assumed to be concentrated. Same as center of mass in case of rigid body. Mass is distributed all over the rigid body, but we considered a point as center of mass at which we considered entire mass of rigid body is concentrated at that particular point. Similarly, here positive charge is distributed inside the molecule. Now we consider a point at which entire positive charge of this molecule is assumed to be concentrated, and that point is called center of positive charge. Similarly, electrons are distributed all over the space inside the molecule, negatively charged electrons. If you consider a point as point at which entire negative charge of the molecule is assumed to be concentrated, then it is center of negative charge. Okay. In case of a molecule, we can consider or we can define 2 points. One is center of positive charge at which entire positive charge of the molecule is assumed to be concentrated, and another one is center of negative charge at which entire negative charge of the molecule is assumed to be concentrated. Now, depending the location of this positive and negative center of positive charge and negative charge, it is decided by the molecule. It is different for different molecules depending on the constituent atoms or elements. The position of center of mass, center of positive charge and center of negative charge will be different in case of different molecules. Now, depending on the position of center of positive charge and center of negative charge in a molecule, dielectric substances, that is non-conducting materials, are classified into two. One is polar dielectrics, and second category is non-polar dielectrics. Okay, polar dielectrics and non-polar dielectrics. Now, in case of polar dielectrics, the condition is like this. If it is a polar dielectric substance, dielectric means non-conducting. It may be paper, it may be plastic, it may be rubber or wood, anything, it is dielectric. Now, if you consider a dielectric substance, inside this dielectric substance there will be large number of molecules. In case of polar dielectric, if you consider a molecule of a polar dielectric, in case of this polar dielectric molecule, the center of positive charge and center of negative charge are separated by small distance. Distribution of charges inside the molecule is such that whenever you consider center of positive charge and center of negative charge inside the molecule, that is 2 points at which entire positive and negative charges assumed to be concentrated, these 2 points are separated by a small distance. We know that net positive charge on the molecule is equal to net negative charge. That means this is equivalent to a dipole, because positive and negative charges of equal magnitude but opposite polarity are separated by a small distance. It is called electric dipole. So that means in case of a polar dielectrics, center of positive charge and negative charges are separated by a small distance. Now, in this case, if you calculate the dipole moment, which is given by 2a into q, 2a is the separation between the charges and q is the magnitude of charge, then this value will be non-zero. Because 2a is not equal to 0, q is also not equal to 0, so 2aq will be non-zero. That means polar dielectrics. What are polar dielectrics? Now, in case of polar dielectrics, center of positive charge and center of negative charges, are separated by a small distance. So there will be separation between the center of positive charge and center of negative charge in case of molecule of polar dielectrics. Now, such molecules are called, if this condition is there in case of a molecule, then that molecule is called polar molecule. The dielectric made up of such type of molecules is called polar dielectrics. What is the effect of this? Positive and negative charges are separated by a small distance. That means in this case, if you consider the molecule of dielectric substance, molecule possesses dipole moment. In case of, the molecule possesses dipole moment. Because of separation between the center of positive charge and center of negative charge, the molecule possesses dipole moment. But if you consider the substance, dipole moment of the substance dipole moment of the dielectric substance, polar dielectric substance, it is equal to 0 because polar dipole moment of the substance is nothing but if you add the dipole moments of individual molecules, then it gives rise to the dipole moment of the substance. If you consider a substance, it will have n number of molecules. In case of polar dielectrics, in each molecule, center of positive charge and center of negative charges are separated by a small distance. That means that molecule possesses dipole moment, or in case of molecule, dipole moment is not equal to 0. So if you consider the material or molecules, each molecule will be like this, plus minus and so on. Now what is the dipole moment of the substance? How to get the dipole moment of the substance? That can be calculated by adding the dipole moments of individual molecules, because substance is made up of molecules. But if you consider the dipole moment of the substance, that is polar dielectric substance, dipole moment of the substance is 0. Why it is so? Because of the random orientation of the molecular dipoles. If dipole moment of this molecule, that is directed from negative to positive, okay, dipole moment is like this. In case of another molecule, the the arrangement will be like this, so that dipole moment will be in this direction. In each case, magnitude of dipole moment is same. If you consider these two molecules, direction of dipole moment of this molecule is direction of the opposite to direction of dipole moment of this molecule. So this cancels with this. In case of this one, this is the direction. In case of this one, this is the direction. These two will cancel with each other. So there will be n number of molecules having dipole moments, but due to random orientation of molecular dipoles, net dipole moment of the substance is 0 in case of polar dielectrics. Okay, polar dielectrics. Reason for this is random orientation of molecular dipoles. Due to random orientation of my molecular dipoles, if you calculate the net dipole moment of the substance, it will be 0. Okay. So this is the case of polar dielectrics. Remember these points. In case of polar dielectrics, center of positive charge and center of negative charges are separated by a small distance. In case of a molecule, therefore a molecule of polar dielectric possesses dipole moment, but if you consider the dipole moment of the substance, it is equal to 0 because molecular dipoles will be randomly oriented, so that if you add the dipole moments of all the molecules, due to random orientation, net dipole moment of the substance will be 0. That is the case of polar dielectrics. Second one is, if you want the examples, okay, examples for polar dielectrics, HCl molecule, hydrogen chloride molecules, then water molecule, H2O molecule. These are all the examples for polar dielectrics. In this case, individual molecules will possess dipole moments. Next, let us consider the second category, that is non-polar dielectrics. In case of non-polar dielectrics, the center of positive charge, in case of a molecule, center of positive charges and negative charge, center of positive charges and negative charges coincide with each other. If you consider a molecule, if this is the center of positive charge, center of negative charge, the position of center of negative charge coincides with the position of center of positive charge. What is the effect of this? Coincide means there is no separation between the center of positive charge and negative charge, or there is no separation between the positive charge and negative charge. If there is no separation between the positive charge and negative charge, dipole moment is given by 2a into q. Here q is not equal to 0, but there is no separation, that means 2a is equal to 0, therefore dipole moment will be 0. Here there is a separation, but here center of positive charges and center of negative charges coincide in case of non-polar molecules. So due to this, as an effect of this, if you consider the molecule of non-polar substance, okay, molecule of non-polar substance, dipole moment, okay, if you consider the molecule, dipole moment of the molecule will be 0 because there is no separation between the positive and negative centers or charges. If dipole moment of the molecule itself is equal to 0, if you consider the substance, dielectric substance or dielectric material, if you consider the dielectric material, dipole moment of the molecule is equal to 0. If you add all those values, once again you will get 0. Therefore, dipole moment of the substance, in case of substance or material also, dipole moment will be 0. Okay, dipole moment will be 0. So, in case of non-polar dielectrics, center of positive charges and center of negative charges coincide. There is no separation between those 2 points. Since there is no separation between positive and negative charges, dipole moment, which is given by separation into magnitude of charge, it is equal to 0. That is in case of molecule. Okay, if you add the dipole moments of the molecules, it gives the dipole moment of the substance. So it is 0, therefore dipole moment of the substance is also equal to 0. Last condition is same for both. Here, because molecular dipole moments is 0, net dipole is 0. But in this case, molecule possesses dipole moment, but random orientation of molecular dipoles results in 0 dipole moment in case of polar dielectrics. If you consider the examples, O2, N2 molecules, etc. Okay, so these molecules or these are the non-polar dielectrics. I think it is clear. Now what we discussed in this case is dielectrics in the absence of external electric field. Okay, dielectrics in the absence of external electric field. We considered 2 dielectric substances, polar and non-polar dielectric substances, and we considered the molecular dipole moment and molecular dipole moment as well as dipole moment of the substance in the absence of external field. When these dielectrics are placed in external electric field, the condition changes that we will discuss now. I think these points are clear. Now all this discussion is in the absence of external electric field. See, what we discussed in the previous case is, if this is the dielectric substance, okay, if this is the dielectric substance, in case of polar dielectrics, positive and negative charge centers are separated by a small distance. The molecular dipoles are randomly oriented. Okay. Minus, plus. Now minus represents center of negative charge, plus represents center of positive charge. So like this, the condition will be like this. There will be random orientation of molecular dipoles. Now this is when external electric field is equal to 0. That means in the absence of external field. Now when this same dielectric material is placed in an electric field, when electric field is not equal to 0, if I place the dielectric substance, that is polar dielectric substance, in the presence of external field, what happens is, now imagine the electric field is directed along positive x-axis. Let it be the direction of electric field. In this electric field, I placed the same dielectric material, okay, dielectric material. Direction of electric field is along positive x-axis. We know that a positive charge experiences a force along the direction of electric field, and a negative charge experiences a force in a direction opposite to that of electric field. If electric field is in positive x direction, plus q charge will experience force along the positive x direction, whereas a negative charge will experience a force in the opposite direction. Okay, we studied that in previous chapter. Now, when this dipole is placed in the external field, now in this case, positive charge of each molecular dipole will experience a force along the electric field, along the direction of electric field, and negative charge will experience a force in the opposite direction. Now if you consider this particular molecular dipole, positive charge experiences a force like this, that is same as electric field, direction is same as electric field, negative charge experiences a force like this. What is the result of this force? These two forces will rotate the dipole, okay, rotate the dipole, so that new position of that dipole will be like this, minus plus. Positive is attracted along the direction of field, negative experiences a force in the opposite direction, so this dipole gets rotated like this. That means this is the new position of dipole. For all the molecular dipoles we can write the same condition, minus plus, minus plus, minus plus. Okay, this will be the situation. Now this phenomenon is called polarization of dielectrics. In the absence of external field, when the electric field is zero, molecular dipoles will be randomly oriented, so that net dipole moment of the substance is equal to zero. But when the same dielectric is placed in the external field, positive charges will experience a force along the direction of electric field, and negative charges will experience a force in a direction opposite to that electric field. Due to that force, each molecular dipoles will align along the direction of electric field, isn't it? All the dipole moments will align, or molecular dipoles will align along the direction of electric field. So now due to this, now if you consider the direction of all the dipole moments, it is same. This is negative to positive, negative to positive, negative to positive, negative to positive. All the dipole moments will have same direction. Now what is the dipole moment of this substance? All the dipole moments are along the same direction. To get the dipole moment of the substance, add the dipole moments of individual molecules. All are along the same direction, no possibility of cancellation. Therefore, in this case, dipole moment of the substance is not equal to zero. In the absence of field, the dipole moment of the substance is zero, molecule is not equal to zero. In the presence of external field, dipole moment of the substance is not equal to zero. At the same time, in case of substance, okay, in case of substance, dipole moment is induced. Okay, dipole moment is induced. Now this phenomenon is called polarization of dielectrics. When a dielectric is placed in the external electric field, due to that external electric field, molecular dipoles will align along the direction of electric field. Due to that, dipole moment is induced in case of the substance. This phenomenon is called polarization of dielectrics. This is the difference in the absence of electric field and presence of electric field. In the presence of electric field, how exactly the polar dielectric behaves. I think it is clear. Now polarization is possible in case of non-polar dielectrics also. See, in case of non-polar dielectric, if I represent a non-polar dielectric diagrammatically, in the absence of external field, when electric field is not there, positive and negative centers coincide, plus minus, plus minus. Okay. In case of molecule, dipole moment is zero. In case of substance, dipole moment is zero. So in case of substance, dipole moment is equal to zero. Now when this material is placed in the presence of, same material is placed in the presence of external electric field, is not equal to zero means there exists an electric field. Let the direction of electric field be same, that is along positive x-axis. Here also what happens is, positive charge experiences a force along the direction of electric field, negative charge experiences a force in the opposite direction. So in the first step, positive center and negative center will move in the opposite direction, which creates the separation between the positive and negative centers. Initially there is no separation between the center of positive charge and negative charge. due to presence of electric field, positive center and negative positive charges and negative charges will experience opposite forces. Due to that, in case of non-polar dielectrics, first of all, a separation is created between the positive and negative centers. Initially it is like this: positive experiences a force in this direction because of that electric field, negative experiences a force in this direction, so this will be the condition. Now a separation is created between positive and negative charges. Initially there is no separation, no dipole moment. Now in the presence of external field, separation is created. Therefore, if you consider the molecule, in case of molecule itself, dipole moment is induced by the external field. Okay, so this is true for all the molecules, minus, plus, like this we can write. In case of each molecule, due to the presence of external electric field, dipole moment is induced, and all the dipole moments will be aligned along the same direction, that is aligned along the direction of electric field. Now if you consider the dipole moment of the molecule, it is not equal to 0. At the same time, dipole moment of the substance, that is the sum of dipole moments of the molecules, it is also not equal to 0. That means in case of non-polar dielectrics, electric field induces dipole moment in case of molecule as well as in case of substance. But in case of polar dielectrics, dipole moment is induced in case of substance. Dipole moment already exists in case of molecule. Okay, so this is the presence of external electric field. Now this condition is called polarization of dielectrics. Polarization of dielectrics. When the dielectric is placed in the external field, the molecular dipoles will be aligned along the direction of electric field. Due to that, dipole moment is induced in case of substance. That phenomenon is called polarization of dielectrics. Okay, I think it is clear difference between polar and non-polar dielectrics. Next. So in the presence of external field, in case of a dielectric substance, dipole moment is induced. In the presence of external field, external electric field induces dipole moment in case of dielectrics. That is true for polar as well as non-polar dielectrics. External electric field induces dipole moment in case of dielectric substances. Now, if P represents, it is not small p, it is not dipole moment. If P represents, if P represents dipole moment, capital P, dipole moment developed per unit volume, okay, P represents dipole moment developed per unit volume of the dielectric substance. That is actually called polarization. Now this value of this P, dipole moment developed per unit volume of the substance, it directly depends on the strength of electric field. Dipole moment developed per unit volume of the substance is directly proportional to strength of electric field. If the applied electric field is stronger electric field, that aligning the molecular dipoles along the direction of electric field, that process becomes easier because strength of electric field is large. That is the meaning dipole moment developed per unit volume of the substance is directly proportional to electric field, or this can be written as, if you replace proportionality by a constant, then it is chi E. into electric field, where this chi E, this is called, or this is given by, it is equal to epsilon naught into k minus 1. Now this term is called susceptibility, electric susceptibility of the substance. Actually, this quantity represents how easily the material can be polarized. Okay, polarization of dielectric. How easily the material can be polarized, that is decided depending on that chi susceptibility or chi E will have different values. Now expression for this susceptibility is epsilon naught, that is permittivity of free space, K is the dielectric constant, so as epsilon naught into K into E, that is susceptibility. Okay, if a material, if a dielectric substance, if it can be easily polarized, under that condition susceptibility of that material will have a large value. If chi is large, susceptibility is large, then such materials can be polarized easily. So this value depends on the material. Polarization is directly proportional to strength of electric field. If stronger the field, polarization is easier, that is the meaning. And this quantity that is called electric susceptibility, that is decided by the material. This measure, it gives an idea how easily the material can be polarized. This is about polarization of dielectrics. Okay, I'll stop the discussion here. In the next class, let us discuss what is the effect of this polarization of dielectrics on the external electric field, and where exactly these dielectrics are used in general. Okay, thank you so much.